Hello, and welcome to our first session on basic statistics and data interpretation. In this session, we will look at the different types of data that you might come across and how best to describe and summarise each type. Our learning objectives are to recognise different types of data, to be able to understand and interpret data summaries, to be able to choose the right sort of graph according to your data type, and to be able to distinguish between normally and non-normally distributed data. Overall, we want you to come away feeling more confident working with data yourself and in understanding other people's data that you might be reading in papers or reports. Here's what we're going to cover in this session. I want to emphasise that knowing the type of data you have is really important because it tells you what you can do with it and the right way to present it. Some of what we cover in this session may be familiar to you already and may seem very basic, but for many of us, a refresher of the basics is a good starting point before we move on to the more complex and interesting statistics covered later in the course. There are two overarching types of data: categorical data and numerical data. All the data you work with will fall into one of these two categories. Let's start with categorical data. This can be split into three types. There's binary data. This is when you only have two categories, for example, yes or no, smoker or non-smoker, and so on. Then there's nominal data. This is when you have more than two categories, but there's no natural order to the categories. For example, different blood types or different ethnicities. Finally, there's ordinal data. This is when, again, there are more than two categories, but with a clear order. For example, months of the year or age groups. In numerical data, there are two subtypes to know. Discrete data is when you have a number, but it has to be a whole number, like a count. For example, the number of people in a household or number of ventilators in a hospital. Continuous data is when it doesn't have to be a whole number, when it can be measured with fractions and decimal points. For example, a person could weigh 55.999 kilograms. In continuous scales, we often have a choice about how precise we want to be, or how many decimal points we think are relevant. So we've talked about the different types of data you might be working with. The type of data you have determines how it can be displayed and how you can analyse it. When our data is categorical, we summarise it using a count of the number in each category with percentages. Now we're going to talk through the main ways to report and display categorical data. Frequency tables are used to display the distribution of categorical data. Here we have a very simple frequency table of gender. This just shows that in a sample of 163 people, 74 male and 89 were female. Note that this table just reports on one categorical variable. Normally, a frequency table would report on several different variables of interest together. Cross-tabulation is for when we want to see the relationship between two categorical variables. This table shows the same data we just saw on gender, but this time subdivided by each person's smoking status. Here's the same data again, with percentages added too. It's much easier to interpret and make sense of the data when we see the percentage in each category too. We can usually choose if we want to display the column percentages or row percentages, and this tends to depend on what you think is the most important information to convey. Here we've chosen column percentages, so the totals in each column of smoker and non-smoker add up to 100%. The key information we're presenting in this table is that there are slightly more male smokers, 53%, than female smokers, 47%. This table is just to show you the alternative way to display the same data, this time with row percentages instead of column percentages. The key information given when we present it this way is that being a non-smoker is more common than being a smoker. This is true for both men and women, but especially for women, because the difference in their category percentages is greater. When we're interested in the relationship between two categorical variables like this, if only to improve our own understanding of the data, it's often worth cross-tabulating it in both of these different ways, because they emphasise different angles. This is an example of summarised data from the trial of e-cigarettes that was mentioned earlier in the course introduction. This is a fairly typical baseline characteristics table, simply describing and summarising the study sample. The three columns on the right-hand side are the three intervention groups. The idea is that we can look at this sort of table to see how similar or dissimilar the groups were. Ideally, in a randomised controlled trial, they'll be similar at baseline, so that only the intervention explains a difference in outcome. Now we're going to move on from tables to graphs. Going back to the gender and smoking data we saw before, we can also present this in bar charts. The height of the bars here is proportional to the frequencies, or the number in each category. The first bar chart on the left just shows the gender distribution. We can see that there are slightly more women than men in our sample. The second bar chart on the right shows the distribution of smoking grouped by gender. This visual display of the same data can be useful because it really emphasises the difference between men and women in terms of their smoking status. Here's the same data again, but displayed in a pie chart this time. Here, the area of the sectors are proportional to the frequencies in each category. Pie charts are useful for showing the relative proportions of different categories within a sample. So the last few slides have covered summarising and displaying categorical data. Now we're going to do the same for numerical data. The two key measures for numerical data are the central tendency, which is a measure of the average, and secondly, the spread of the data, how much it's spread out around that average. We'll go through each of these in detail. There are three measures of central tendency or average. These are probably familiar to you. The mean we calculate by adding together all of the values and dividing that total by the number of values, or the number in our sample. The median we calculate by arranging all the values in numerical order and identifying the middle one. The mode is simply the most frequently occurring value. This is a histogram showing the length of hospital stay for 19 patients. Looking across from left to right, we can see that one patient stayed for 3 days, 2 patients stayed for 4 days, 1 patient stayed for 6 days, and so on. The arrows show the central tendency of the data according to the 3 different measures. As you can see, each one gives a different answer, so picking the right one is important. We'll go through these on the next slide, and later we'll also cover how to pick the right one. So firstly, the mean. We've got this by taking each of the values displayed in the figure, adding them all up and dividing the total by 19, because we have data on 19 patients. Note, we have one instance of the value 3 because only one patient stayed for 3 days. We have 2 instances of the value 4 because 2 patients stayed for 4 days, and so on. Now the median. Here we've lined up all the same numbers in order and identified the number in the middle. Here, as there are 19 patients, the number in the middle is the 10th value, which happens to be 10. If you have an even number of values, then you end up with 2 middle values. In those cases, we would just take the number that lies halfway between the 2 middle values. For example, 10.5, if the 2 middle values were 10 and 11. Finally, the mode, the value that occurs most frequently or most commonly. Here we can see both from the figure and from lining up the values that 8 days in hospital is the most common length of stay. In this example, because the data are skewed or not normally distributed, the most appropriate central tendency measure to use is the median. We'll come back to this later. So we've just been talking about measures of central tendency or averages. Now we're going to go through measures of spread of numerical data. The most intuitive to start with is the range. This is just the difference between the largest and the smallest value of a variable. When we report the minimum and maximum number, we are reporting the range. For example, a sample of people aged 20 to 60. Percentiles, quartiles, and the interquartile range are all calculated by splitting the whole range of data into hundredths or quarters. We'll go through these in more detail in a minute. The standard deviation is a standardized measure of the spread of the data around the mean. Again, we'll go through this in a minute, and please note the standard deviation is probably the most complex bit of this first session, so don't worry if it feels a bit abstract at first. The growth chart shown here will be familiar if you have or work with children. It's a sort of prediction chart of the birth weight of female babies between 22 and 44 weeks gestational age. This and other growth charts will have been constructed by collecting data on large numbers of female babies and plotting the observed birth weights for each week of gestational age. It's used to identify whether a baby is particularly above or below average weight for their age. We can see from this chart that at 40 weeks gestation, the median weight is around 3,400 grams. Babies heavier than 4,000 grams are in the top 10% of weight for their age because they are above the 90th centile. Babies smaller than 2,900 grams are in the bottom 10% of weight for their age because they are below the 10th centile. Quartiles are like percentiles, except that the whole range is divided into quarters instead of hundredths. Say this is data on recovery time after eye surgery. The x-axis along the bottom is the number of days taken to recover. The height of the line corresponds to the frequency, or the number of patients who have taken that many days to recover. We can see the median here, which you remember is the middle of the data, or 50% of the way along, is about 8 days. The red lines split the data into quarters, or quartiles. The smallest 25% and the highest 25% are at either end, and what we call the interquartile range is the middle 50% of the data. We can see here that the middle 50% of the data, the interquartile range, is between about 5.5 and 11 days. Sometimes we display medians and interquartile ranges using a graph called a box and whisker plot. Here we have 7 box and whisker plots describing the sleep patterns for a group of people by day of the week. Here the middle line in each box shows the median. The top and bottom edges of each box show the full interquartile range, the middle 50% of the data. The whiskers, or little T-shapes at each end, show the full range. The key interpretation to take away from this graph is that people tend to get most sleep on Friday and Saturday night, but other nights are pretty similar. So we've talked about the range and interquartile range and percentiles. Now we come to the final measure of spread of numerical data, the standard deviation. Remember, this is probably the most complex bit of our first session, so don't worry it was hard to get your head around at first. Essentially, this is just another way to measure the spread of values around the mean. Think of it as a bit like the average distance from the mean. Specifically, it's a standardized measure of the variation or deviation of values around the mean. For example, this graph shows the IQ scores for 29 people. The mean IQ is 100, shown in the dotted line. Each dot shows one person's actual IQ score. We can see how each of these individual values deviates from the mean, how far it is above or below the mean. Looking from left to right, we can see that person 1 happens to have a score of 100, so they have 0 deviation from the mean. Person 2 has a score of 118, so they are 8 points above the mean. Person 3 has a score of 94, so they are 7 points below the mean, and so on. We use the distance of each individual value from the mean to calculate the standard deviation, or average distance from the mean. This is the equation we use to calculate a standard deviation. In reality, you never need to do this for yourself. A computer will always do it for you. We'll talk through it just to show where it comes from. For some people this is useful. If it's not, please feel free to ignore it. So here are the steps. First we calculate the mean. Then we take away that mean number from each individual value or each data point. Then we square each of those results. That's just to eliminate the positive or negative signs. Then we add all of those together and divide by the total number in the sample, just like we did to calculate the mean. Finally, we take the square root of the final result, and that is the standard deviation. As I said, the calculation itself is not the important thing. All you need is to have an understanding that the standard deviation is another measure of how the data is spread out around the mean. The reason that standard deviation is very useful in statistics is that it's standardized. In any normally distributed data, certain properties of the standard deviation will always hold. The curved line here shows normally distributed data. It's considered normal because it's symmetrical around the mean, here a mean of 0, and it's bell-shaped. A normal distribution is sometimes called a bell-shaped curve. We can standardize the mean of any normally distributed data to 0. The +1 and -1 on the line shows the area of one standard deviation either side of the mean. About 68% of your data will lie within one standard deviation either side of the mean. The +2 and -2 shows the area of two standard deviations either side of the mean, and about 95% of your data will lie within two standard deviations of the mean. Formally, 95% of your data will lie within exactly 1.96 standard deviations of the mean. This will come up a lot in the next session on confidence intervals. Here's an example of the standard deviation of IQ scores. The mean IQ is 100, and we can see that one standard deviation is 15 IQ points. From this, and the fact that the data are normally distributed, we know that 68% of the sample have scores between 85 and 115, because that covers the range of one standard deviation, or 15 IQ points, either side of the mean. Similarly, we know that about 95% of the sample have scores between 70 and 130, because that covers the range of two standard deviations, 30 IQ points, either side of the mean. Here is another example of the distribution of IQ scores in a different sample of people. This sample of people have the same mean IQ of 100 like before, but there is a bigger standard deviation, 22 rather than 15. You can see that this distribution is wider and flatter than the shape in our last example. It's still normal, it's still symmetrical and bell-shaped, but there's more variation in scores. Scores are more spread out around the mean. In this case, 95% of the sample have scores between 56 and 144, because that covers the range of two standard deviations, or 44 IQ points, either side of the mean. This plot is just to highlight how the two samples of people differ. The blue line, with a smaller standard deviation, has more values concentrated closely around the mean. The red line, with a bigger standard deviation, has a wider spread of values. There's more variation in IQ scores. So now we've talked through all of these ways to summarise and describe numerical data, using the measures of central tendency and spread. We need to know which are the most appropriate ones to use in any situation. This is what we'll cover next. To decide the best way to describe numerical data, we first need to know how it's distributed, or what its shape is like. The key question is it normally distributed or not? We've talked a little bit about normal distributions already. So the best way to do this is to make a histogram of your data. We can see that the first shape on the left is normal or bell-shaped. It's also sometimes called a Gaussian distribution. Note that it's roughly symmetrical. It doesn't have to be perfect, just approximate. The shape on the right is not normally distributed. We can see that most people have low scores for this variable because the scores look bunched up on the lower end of the scale. But then there's a tail of a fair few people with higher scores trailing off to the right, higher end of the scale. This is skewed data. There's lots of other ways for data to look, but the important thing is whether it looks normal and symmetrical or not. It's also important to know that how much data you have, or how big your sample size is, affects how well your data creates the bell shape. The picture on the left is data on 1,000 people, and it's clearly normally distributed. The picture on the right is a sample of just 30 people, randomly picked from that same original sample of 1,000. In this small sample, you'll see that it's much harder to spot normality. Once we know the distribution of our data, we know how best to describe and analyse the data. If it looks approximately normal, it should be safe to use the mean and standard deviation and analyse the data with standard parametric tests. Statistical tests are covered in the next sessions of the course. If the data does not look normally distributed, it's often safer to use the median and range or interquartile range and analyse the data with alternative sorts of tests. When we're interested in the relationship between two numerical variables, a scatter plot can be a very useful graph. Here a scatter plot shows the relationship between height and weight. As you would expect, they're correlated. In general, tall people tend to be heavier and small people tend to be lighter. When two numerical variables generally increase and decrease together, it's called a positive linear association. The scatter plot on the right just shows another dimension. Here the red dots are women and the blue dots are men. We can see that there are slightly more women at the shorter, lighter end and slightly more men at the taller, heavier end. On average, men tend to be slightly taller and heavier than women, but there's a lot of overlap. Usually scatter plots are much more scattered than this example shows. So far, we have mostly considered how to summarise a single variable. However, often we're more interested in the relationship between two variables. For example, does drinking coffee cause high blood pressure? Does drinking red wine protect against heart disease? The first step is just to investigate whether there seems to be any association between the two variables of interest. Association is a broader term that does not imply causation. Just indicates if two things tend to go together. This will be the focus of the next part of the course. Finally, I just want to introduce the terminology used when we're investigating whether one thing affects another thing. The exposure is the thing that we think has an effect. The outcome is the thing that we think might be being affected. For example, we know that exposure to cigarette smoke increases the risk of the outcome lung cancer. exposure to unprotected sex increases the risk of the outcome STDs, or the outcome of pregnancy. You can see listed here some of the other names also used in place of exposure and outcome. Here are some examples, and no doubt you can add your own to this list. In the first example, if you were an orthopaedic surgeon, you'd probably be interested in finding out the best sort of hip replacement for your patients. Your research question might be whether metal and metal replacements were better or worse than ceramic replacements. You could define better in terms of the patient's reported pain or function at 6 months after surgery. Here, the type of hip is the exposure, and patient pain at 6 months is the outcome. Going back to data types for a moment, the examples listed here are binary exposures and numerical outcomes. This is a really common experimental design. However, we can equally explore relationships between numerical exposures and categorical outcomes, or any other combination of data types. For example, the number of months someone has been prescribed antipsychotic medication would be a continuous numerical exposure. Their later risk of developing diabetes or not would be a binary outcome. That's the end of this session. If you have any questions, please write them down and bring them along to the live question and answer Zoom session. Thank you for listening, and I hope you enjoy the rest of the course.